This tutorial is about the elliptic partial differential equations, and in this tutorial we will learn how to solve a simple elliptic partial differential equation. Generally, while solving the partial differential equations, we encounter linear system of equations, ax equal to b type equation, that we can solve with any of the methods that we have learned in the mm, uh, in linear algebra. Here we will use the iterative solution technique. This technique is similar to the previous tutorial on boundary value problems with the finite difference scheme. So we begin with the example. We have a simple partial differential equation, partial square u partial x squared plus partial square u partial y squared equal to 0. For simplicity, let's assume the number of steps in m and n in x direction and in y direction are same, equal to 4. So this means h squared over k squared equal to 1. We have in this problem the boundary conditions like ux0 equal to 0, which means for all points along x-axis where y is equal to 0, so we have a value 0 for the dependent variable u. Similarly, for all points ux 0.5 at the boundary 0.5 marked by the y value 0.5, so this is 200x. And similarly, we have the this is the lower boundary condition. Here x is equal to 0 and y is variable. So for all points in y direction where x is equal to 0, so this is generally the y-axis. And the right boundary, so u 0.5y, for all points we have 200y. So the value is governed by this 200y value. Let's draw these boundaries in the Microsoft Excel sheet. I have developed a frame for you. Generally, we keep the x-axis as the horizontal axis and y as the vertical axis. But with respect to this demonstration, you have to rotate this figure about 90 degrees. So here x-axis values are increasing in the downward direction, and y-axis values are moving in the x direction, horizontal direction. That is the way this demonstration has been developed. Okay, so let me draw the first boundary, ux0. So for y values equal to 0 and for other values of x, by the way, this is the blue marks the domain of u variation. So I make it here u equal to 0. So this is the boundary ux0. So x values are changing and y values are fixed. So we have all values equal to 0. Now u0y, where y value is equal to 0 and x values are changing. Well, pardon. Sorry, this was the left boundary. Let me repeat that. ux0, x values are changing. Well, we don't have to rotate the figure. So ux0, so x values are changing and y values are equal to 0. So we have this type of boundary values. And similarly, u0y, when x values are 0 and y values are changing, so we have these values for the boundary. Now the right boundary, when x is fixed, so 0.5 and y, so it is equal to 200y. So x value is fixed as 0.5 and y values are changing as 200 times y. So I generate these values. First value will remain the same. So here I will keep 200 times the y value. So it has been picked from its respective position. So these are the boundary values. And now the lower boundary. So where x is changing and y is fixed. So x 0.5. When y value is 0.5, so it is 200x. So this will mark y value is 0.5. So all the rest of the values would be 200 times the x value, and correspondingly we will generate all the boundary values. So boundary values have been generated, and we have the unknown values in between, and these are 16 values in between, since we have adopted the step size equal to 0.1. Now in the finite difference method, we have to only provide the numerical equivalents for the derivatives. So we have two such derivatives, second order derivatives of u with respect to x and y, the spatial domain. So for spatial domain, we have index I moving in x direction, and for y axis, for y variable, we have utilizing index j. So when we differentiate with respect to x, so the y variable would remain fixed. So therefore, you can see the derivative definition. So ui plus 1j minus 2uij plus ui minus 1j over h squared, where h is the step size in x direction. We have the corresponding error term, and error term should be evaluated if possible by keeping y fixed. However, it should be the variation of function to the fourth order in x. So this is the definition for partial squared u over partial x squared at point xij. So it means the derivative at the central point at point ij is computed by using the values, which is one value which is at the left, one value is at the right, and one at the central point uij. Similarly, the derivative with respect to y, second derivative, in this evaluation we have to keep the x coordinate fixed, and there will be the variation in the y coordinate, which is represented by the subscript j. So we have uij plus 1 minus 2uij plus uij minus 1 over k squared, where k squared is the step size in y direction. So when we provide these equations in the main equation, this definition defines the differential equation in difference form at point ij. So our point of interest is point ij. So the value at point ij will come from the surrounding 4-point values. So we can also write this one in mathematical form as for this matrix. So we have the coefficient of uij equal to 4, and for all the surrounding points we have the coefficient minus 1, and for this equation we have on the right hand side equal to 0. So this is the equation. So if you like, you can compute that uij will be equal to the average value of the data points surrounding this value uij. So we will have uij minus 1 plus you will have an expression like ui minus 1j plus ui plus 1j plus uij minus 1 plus uij plus 1. So it is the weighted average of these values. In the method for solving these equations, we have to write the equation for all the interior points. Like we have to write this equation for this point, for this point, in all 16 points. We have to write this equation, and we will construct the system of equations. Of course, when some of the values are near the coordinates, so we will have some of the values known from the boundary. So we will keep those values to the right hand side of the equation, and our system would be finally ax equal to b. However, we can find the solution on the basis of the iterative method, that we first use a guess values for this matrix, for these interior points, not for matrix. So for all the interior points, let me start with the initial guess approximation. For example, let me select a value 40. Let's select this value for all the points, interior points. This is not the intelligent guess. However, let's work with that. So we have written the finite difference equation form in the iterative form. So it means it is the value at a point will be equal to the average value of all of the surrounding nodes. So we have assumed some values from so we have a value at uijk plus 1, and the next iteration value would come from as an average value from the surrounding points. So let's implement that. So before doing that, we have to copy the boundary values. So let me copy these values here, and all these values. These values should be copied carefully. It's a special paste option, which is for values, and the final boundary values with the option of paste values. Now let's implement the algorithm. So the new value at uij will be equal to the surrounding neighbors sum of the values. Let me read these values. The first value was uij minus 1. This was ui minus 1j. Then this value uij plus 1, and this value uij plus 1, and this value is equal to ui plus 1j. So a weighted average for this, so divided by 4, so we call a new value. And similarly, we will repeat that strategy for all these surrounding points. So we have the new values after first iteration. We can also calculate the error. So error value should be equal to the corresponding value of u in the current iteration and the previous iteration. So let me write here absolute value. So value uij in the new iteration and the value in the previous iteration. Okay. And the same I have to repeat for the all of the interior node points. So the next step is to repeat this calculation and keep on until the error is smaller and smaller to our convergence criteria. So I will copy this value in Microsoft Excel sheet, we can perform this calculation in this fashion. And we paste special the values, and the values would be updated. And again we can do this process. So for smaller problem, yeah, I had to paste with the paste special options. So after doing that again and again, finally our solution will converge. So this was the solution of elliptic partial differential equation. And instead of constructing the whole 16 by 16 matrix, we implemented the Jacobi strategy. On similar lines, the partial differential equations are solved for other types.